we know in degrees, this is going to be an easy question. If here's my initial ray, and I open it up, and here's my terminal ray, what is that in degrees? 180. We know that. In radians, it's approximately 3.14. So that's in radians. Does 3.14 ring a bell for you guys? Pi. Correct. That is pi. Okay? So if that's pi radians, or 3.14 radians, if I were to do a full rotation, what would that be? Approximately 6.28. What about in terms of pi? 2 pi. Exactly. So here's one of the first facts. Pi radians equals 180 degrees. 2 pi radians equals 360 degrees. And just for the sake of kind of giving you a parallel thought process, even though this has nothing to do with what we're doing, I'm going to say 0 degrees Celsius equals 32 degrees Fahrenheit. Just so you understand the equivalence, but the fact that we're on 2 totally different scales. Okay? Where would you guess, if this is 3.14 radians, what's this? Calculators. Approximately 1.57. Very good. Now, you're not going to deal with that number a lot, but I'm trying to get to 1 radian. Where would 1 radian be? Which quadrant? First. Okay, so you'd open up. That would be about 1 radian. 0 radians. Okay? So, by definition, 1 radian, and this is kind of a weird concept, and maybe I'll do, I wish I had a website that would do this, because I'm going to try to do this hard. If you think about like a circle, okay, and your central angles, and I'm going to let this be the initial ray, okay? 1 radian is when the arc length is the same size as the radius. So does that look like this length is the same as that? No, this would need to be bigger, right? So, and it's kind of hard to envision. Let's go here. Do you think this arc length is the same size as that? This arc length's too big, right? Okay, so we have to go smaller than that. How about that? Do you think that is the same size as that, or is this too small, too big? Still a little bit too small. How about we open it up a little bit more? How about like this and that? That would be good. Approximately, right? So that is 1 radian when your arc length is the same size as your radius. So as soon as that happens, that's that measure. Okay? And this formula that we have here kind of gives us that info. I wanted to do a little bit of an animated illustration there, that's why I did that. But this formula tells you that your theta, that's in radians. This has to be in radians. This does not apply to degrees. Theta radians, remember theta is just our variable, but a Greek letter, so x radians we won't say, we'll say theta radians, equals S. S stands for the arc length
over r. That stands for the radius. So in my illustration, when your arc length, let's say the arc length was 5 inches, and your radius is also 5 inches. 5 over 5 is 1, and in that case, theta would be 1. Okay? This formula just very quickly is rearranged. If I just didn't like the fraction and I wanted to get rid of the divided by r, if I multiplied both sides by r, it turns into this formula, which we're going to refer to this version of it more often because it's the SOAR formula, because theta kind of looks like an O, right? So if I say the SOAR formula, that's your formula that connects arc length with the radian measure of an angle with the radius. Yes? Correct. Yep, exactly. So, and actually, if I went back to that illustration, and going back to the fact that that's 3.14, if I have this initial ray, and I open it all the way up here, right? This arc length, let's pretend this is a radius of 1. This arc length is 3.14 times that. That's why this angle measure is pi radians or 3.14 radians. Because your angle measure is the arc length divided by the radius. So if your arc length is 3.14 divided by your radius, which is 1, that's the angle measure. Okay? I mean, what if the radius is 5? If the radius is 5, well then this is going to be 15 point something. Right? So it's that we know that if the radius grows, then the length to get around the circle grows. Versus if you have a radius of just 1, the length to get around is just 3.14 times that. So the ratio of the arc length to the radius gives you your theta value. Okay, that's the meaning of a radian. I don't know how often we're going to use that, but we will use this formula a lot. You'll see in some word problems when you're given 2 of those 3 pieces of information and you're asked for the third. One of the big things about this formula, though, is if they give you that theta is 30 degrees, you do not plug in 30. We will have to get the equivalent of 30 degrees in radians, because this theta from this formula is always radians. You cannot plug in a degree measure. You have to convert the degree measure to radians first. Okay? Just like you convert temperatures from Celsius to Fahrenheit and vice versa, we'd have to convert the degrees into radians, and I'll teach you how to do that today. So I think in this next section, I was kind of going to touch on and explore a little bit, Nathan, what you just mentioned. We're going to skip that for now. I'll come back to that if we have time. But let's just jump right down to an example where we're going to use the SOAR formula. Determine the number of radians that the minute hand of a clock passes through if it has a length of 5 inches and its tip travels a total distance of 13 inches. Now this is a clock, so I'll say, let's just pretend our hand of the clock is starting there. It says that it has a length of 5, and the tip, as it's rotating around, is going to go around 13 inches. So let's just say that's about 13 inches. So that's 13 inches. The question is, determine the angle measure in radians. So that's our theta. 5 is our radius, and 13 is our arc length, or our S. So just copy down the SOAR formula, plug in what we know. 13 equals theta times 5, and solve for theta. Just divide both sides by 5. So we get 2.6. Which is not 3.14, which would be a half circle. We all can agree that that's not quite a half circle rotation. Okay, that's 2.6 radians. Approximately what degree measure would you guess? Not 180, right? Less than 180. Over 90 though, don't you think? Over 90, less than 180, and that's about as accurate as we can get. And we'll talk about how to convert that to degrees in a minute. Okie doke? All right. B's more of the same. Well, let's just talk about it now. How do you change the appearance of something without changing the value? What do you have to multiply it by? You know? We've done it a couple times this year. We've changed the appearance, but we won't change the value. What's the only thing you can multiply by without changing the value? 1. So this here is 2.6 radians. We're going to convert it to degrees right now. We're going to multiply this by 1, but we're going to do it in a very tricky way. Okay? Do you all agree that 24 hours divided by 1 day is 1? Right? Because this is something divided by itself. So that's 1. We're going to do a similar thing here. We want to get the radians to cancel because it's currently in radians. We want to go out of radians. So we're going to multiply by some number of radians as our denominator and some number of degrees as our numerator. But we're going to do it in a way so that these are equivalent values so that you're dividing something by itself. So let's go with what we started with. Pi radians. How many degrees is that? 180. So we're multiplying by 1, but in a very tricky way. Evan, what are you doing? Sorry, I thought you were on your phone. So just on your calculator, you would just type that in. 2.6 times 180 divided by pi. 140, let's go to the nearest degree. 149 degrees. So there's your conversion rule. From radians to degrees. So it was currently in radians. So what really just happened is your radian units canceled. We got 149. Okay? The next section is degrees, and we're going to go to radians. Yep. When you convert radians to degrees, do you always use 180 over pi? 180 over pi. Mm-hmm. Always. Yep, always from radians to degrees, use 180 over pi. On the flip-flop, if we're going degrees to radians, we're going to do the pi on top and the 180 on the bottom. And here's why. So this is 90 degrees. We're trying to get out of degrees. So when we multiply this by something, we want the degree here to cancel with the degree in the denominator here. So we put the 180 degrees in the denominator and the equivalent radian measure, pi, in the numerator. So now your degrees cancel, and we just have 90 pi over 180. Now, there's two ways to present this answer. One is to do 90 pi over 180 and just reduce, which would be pi over 2. Thank you, Isaiah. That would be one way of presenting it, or you could actually do it out. Pi over 2, or 90 pi divided by 180, and get 1.57. You're going to see in this chapter, we keep things in terms of pi. I mean, these are the same thing, but we keep things in terms of pi. So you can see where this would get confusing. Oh shoot, do I multiply by pi over 180 or 180 over pi? Think about what you want to cancel. If you want radians to cancel, then put the pi radians in the denominator and the 180 up top. If you want your degrees to cancel, then put your 180 degrees in the denominator so that they will cancel and that you're left with the radians from the numerator. Does this make sense? Okay? All right, flip over to the back. Here we're converting common radians into degrees. So 5 pi over 6, we're going to multiply by, we want the radians to cancel. So we're going to put the pi radians in the denominator and the 180 degrees up top. So here's what's nice about this, and this is typical. Your pi's cancel. So now it's just 5 times 180 divided by 6. And we get 150 degrees. Yep. Yeah, before multiplying? Sure. Yep. He's saying 6 and 180, he noticed, is 1 and 30. 5 times 30 is 150. Yeah, you could do all that. Okay? Now, let's think about this. We'll do more of this tomorrow. But don't go ahead of me. Watch this, because this is a good conceptual thing that can help make sense of a lot as we move forward here. If this is pi radians, yet our denominator is 6, can't I just think of this as 6 pi over 6? Isn't 6 pi over 6 the same thing as pi? But the reason I would do 6 pi over 6 is because this is 0. This is 1 pi over 6. This is 2 pi over 6. Here's 1 pi over 6. Here's 2 pi over 6. Here's 3 pi over 6. Doesn't that make sense? Because 3 pi over 6 reduces to pi over 2, and that's half a pi. Here's 4 pi over 6. Here's 5 pi over 6. And here's 6 pi over 6. What we did is we took this pi, this full rotation, and we just split it into 6 parts. Right? There's 6 pieces. Piece 1, 2, 3, 4, 5, 6. Does that make sense? So 5 pi over 6, which is right here, you can see why 150 degrees makes sense, right? Doesn't that look like about 150 degrees? If pi is 180, we all agree with that, right? Pi is 180. If you split pi into 6 parts, what is 180 degrees split into 6 parts? 30, right? So that's a 30-degree angle. There's 30 more. There's 30 more. Doesn't that make sense? 30, 60, 90 gets you to your right angle. And then here's 30 more. That's 120. Here's 30 more. That gets you to 150. And here's 30 more. That gets you to 180. So what's the reference angle here, by the way? 30, because we know that's 150 and that's 180, so 30. What about in terms of radians? If this is 5 pi over 6 and this is 6 pi over 6, what's the reference angle? How many pi's over 6? What's the difference between 5 pi over 6 and 6 pi over 6? 1 pi over 6, right? A reference angle of 30 degrees is the same as a reference angle of pi over 6. Pi is just 180. 180 divided by 6 is 30. Okay? We will do reference angles in terms of degrees like you saw yesterday, but we will definitely do reference angles in terms of pi a lot. Okay? So that's that. Let's jump down to exercise 6. Again, these are radians, but these radians don't have a pi attached to them. That's not a big deal. It's just this is 5.8. You might want to write the word radians to remind yourself that that's in radians. If it's in degrees, there would be a degree symbol. If there's not a degree symbol, you just assume it's in radians. So here's 5.8 radians. Connor, what am I multiplying this by? 180 over pi. 180 degrees over pi radians. So your radians will cancel and you'll just do 5.8 times 180 degrees. divide that by pi, and you get approximately to the nearest degree 332. Now, again, don't worry about the other parts B and C. Let's talk about why this makes sense. Going back, this is 0 radians. How many was this? No. 3.14. If we kept going the full circle, how many is this? 6.28. So what's this in between then? Well, we said, let's go this way. 0, what was this? 1.57. So what's 1.57 more here? 7.1. Is that right? So 5.8 is in between these two. Agreed? So our rotation makes our terminal ray be in the 4th quadrant. Can we agree that 332 is also in the 4th quadrant? Because that's 270 degrees versus 360 degrees. Yeah, that makes sense. Okay? Just like our degrees in the negative direction, all is the same. So if I were to open up this angle, here's 0, here's negative 1.57, here's negative 3.14, and so negative 2.5, can we all agree, is going to be in here somewhere? Yes? Reference angle is going to be the difference between terminal ray and this x-axis, right? All good stuff? Okay? If we were converting this, we would multiply it by 180 over pi. So I'll do that, negative 2.5 times 180 divided by pi, and we get negative 143 degrees. We can all see, right? Negative 143 degrees. Here's negative 180. So negative 143 makes sense. It's falling in that 3rd quadrant. Okay? And then the last section. 2 radians. We already know this is 1.57 and this is 3.14. So, John, what quadrant is this theta going to end in? Good. What's the reference angle? Cameron. Nope. Here's our terminal ray. Here's our x-axis. What's the reference between them? No, you're going back to the y-axis. I don't want that. I want this angle between 2 and 3.14. Perfect. Okay. Negative 1. This is negative 1.57. So what quadrant is negative 1 in, Grace? Yep. And what's my reference angle, Nate? I think, where are you getting that from? Nope, I think you're doing again between the y-axis. The reference angle is the terminal ray to the x-axis. But it's always positive. Reference, yep, so just one. Reference angles in degrees are always between 0 and 90. In radians, always between 0 and 1.57. And then we're going to do more with radians when they're in terms of pi. Like this was pi over 6 was this reference angle here. We'll do more of that in the days to come. But this reference angle is just 1. How about 4? So we've got 1.57 and 3.14 and what was this number? 4.71. I cheated and looked up. And this is 6.28. So where is 4? What'd you say, Mason? 3rd quadrant. And the reference angle? .86. Very good. That's the difference between 3.14 and 4. And then lastly, 6.3. What's a full circle? 6.28. How much past that are we going? 0.02. So there's 6.3, and so your reference is 0.02. Good. Good, good, good. Okay? I want to go back up to this top part. Not so much to convert, because we all can just multiply by 180 over pi. But let's talk about where this is. See, this denominator is 2. So when I create my rotation diagram, and normally this is pi, if my denominator is 2, I'm going to think of this as 2 pi over 2. So what is this? 1 pi over 2. 2 pi over 2. What's this? 3 pi over 2. And what's this? 4 pi over 2. What is 4 pi over 2 reduced to? 2 pi. Doesn't that make sense? Because that's a full circle. So 3 pi over 2 is going to be right there, which now we should easily be able to tell us is the same as 270 degrees, right? We would have gotten the 270 degrees by multiplying by 180 over pi. I'll show you that. 180 over pi. Your pi's cancel. Your 2 and 180 become 1 and 90. And 3 times 90 is 270. What is the reference angle of this in terms of degrees? 90. What is the reference angle of this in terms of radians? What's the difference between 2 pi over 2 and 3 pi over 2? Pi over 2. From 2 pi over 2 to 3 pi over 2, that's just 1 additional pi over 2. And then in C, if the denominator is 4, how am I going to label this? 4 pi over 4. Excellent. What would this then be? 2 pi over 4. Doesn't it make sense because that reduces, right? That coincides with pi over 2, which is what that always is. What would this be? 6 pi over 4, and what would this be? 8 pi over 4, which reduces to 2 pi, which is that full circle. So in this particular case, 3 pi over 4 is right here, yes? Between 2 pi over 4 and 4 pi over 4. So that's 3 pi over 4. What's the reference angle? 1 pi over 4. From 3 pi over 4 to 4 pi over 4 is 1 pi over 4. So what happens when you have this split into fourths is you've got 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. Look at that pi. How many pi pieces did I just split it into? Right, I split it into fourths. Okay? We'll do more of that in the days to come. But that was all good stuff. Remember, your corrections are due tomorrow. I'm here after school if you need some help with those. And your homework is coming around.